Okay. 2.2, instantaneous rate of change. So the rate of change at an exact point on a curve, y equals f at x, is called an instantaneous rate of change. Okay, so this is key, exact point, 1 point. It's not 2 points, it's not average. Okay, it's equal to the slope of the tangent line at that point. So let's talk about what is a tangent line first. So a line that touches the graph at only 1 point within a small interval, right, of a relation. So for example, on this is the tangent. Okay, I understand that eventually, like if you extended this point, it's going to go through the curve again. That's fine, because we're not looking over here. We're focusing on like this area here. So we're saying, okay, this is the tangent. Okay, it could, but does not have to cross the graph at another point outside of that interval. So outside of like immediately where we're looking. Okay, so instantaneous rate of change. The instantaneous rate of change is the exact rate of change of the function y equals f at x. So whatever function we're talking about at a specific value of the independent variable x equals a. So whatever x is. It can be estimated using average rates of change for small intervals of the independent variable very close to x equals a. So in our investigation, we had our x equals to 6 that time. So we know that we had a curve, it was a quadratic, it was an x squared curve, and we had this point at 6. Okay, so what this is saying is the IROC is the exact rate of change right at this point. But what we usually do is we usually use average rates that are very, very close to the 6. Right? And that's where we get the 5.999 from, and that's where we get the 6.001 from. So instead of using the tangent, we are actually going to use the secant from 5.999 to 6. There is a line there. It may be so microscopic that you can't see it, but if you zoomed in enough, it's going to be there. And we're going to find the average rate of change between 6 and 6.001. Okay, so let's talk about methods of estimating the IROC. Okay, interval strategies. So this can be used when data is given in a table of values. So there's 2 different approaches here, whether they give you a table of values or whether they give you like an equation, okay? So there's something called preceding and following interval method. So this determines, what we have to do is determine the mean value of the rates of change of the preceding interval and the following interval. So mean, if you haven't taken data, this means average. So what is a preceding interval? A preceding interval is an interval of the independent variable of the form. So I'm going to show you the domain here, and then I'm going to explain it in words. So, well, I'm just going to explain it in words. Whatever x is, okay, so an interval of the independent variable of the form a minus h and a. So x is between some number minus an h and a. So our a in the investigation was 6. So our interval would be maybe 5.999 and then 6. So, and where h is a small positive value. So what that would mean is h would be 0.001. We would take 6, like a minus h. We would take 6, we would subtract this really, really small number from it, and we would get 5.999. And then that's what our interval would be. So when you think of the word preceding, you're thinking before. So think of the word before. Now, following interval, same thing, It's just on the other side. So when we're thinking about the word following, we're thinking about after. Okay, so this is the exact same thing. There's going to be some interval between A, so for example 6, and A plus H. Well, in this case, A is 6, H, again, let's take H to be super small, 0.001. Okay, so then that would mean that we're finding the average rate of change between 6 and 6.001. All right, method 2. So this one, for sure, if you get a table of values, you have to use it. I may ask you on a test, use preceding. I may ask you use following, or I may ask you for centered, okay? So centered interval method. So this is when we calculate the average rate of change. Again, even though we're using tangent and IROC, we're actually going to calculate the AROC, average rate of change, using the smallest possible centered interval. Okay, what this means, so a centered interval is in this form here. So here's the domain. So for example, 6 minus 0.001 or 6 plus 0.001. So what we would do is we would plug in the points 5.999 and 6.001, and then we would find the average rate of change with those 2 points. Okay, please note some of these questions and on your test, they may say H is 0.1, H is 0.01, or H equals 0.001. It's usually one of these three. Okay, so it may be specified, so just read the question. Okay, example 1. The following table represents the temperature of an oven as it heats up from room temperature to 400 degrees. Okay, so we have time, we have temperature. Estimate the instantaneous rate of change exactly at 5 minutes. So this is what we're going to be talking about. Okay, so if we're given a table of values, you want to make sure that you're likely going to use preceding and following interval method. So let's chunk this down. So let's go preceding. Okay, and preceding would be from 4 to 5. Okay, so we're going to talk about the interval when x is between or n equal to 4 to 5, and then we're going to find the following interval. Okay, and the following interval would be 5 to 6. Okay, and what that's going to look like is we're going to find the average rate of change between these 2 points. So we're going to sub in f at 5 minus f at 4, and then we're going to do 5 minus 4. And likewise, we're going to go f at 6 minus f at 5. And then we're going to go 6 minus 5. Okay, so when we take a look at f at 5, we get 275. And you can just cross-reference it. There's no equation to actually plug it into. So I get 275 minus 250 divided by, well, we have 5 minus 4, which is just 1. So I get 25 degrees Fahrenheit per minute. Okay, f at 6 is 310. F at 5 is 275. And the difference in these two is 1. So then I get 35 degrees Fahrenheit per minute. But going back to the previous page, it states for the preceding and following methods, we take the mean. So the instantaneous rate of change, that's what we're going to call it, is the average between 25 and 35. So we add them and divide them by 2. So we're going to say mean value. Mean also is called the average. 3, 4, 5, 6. So I get 60 divided by 2. So our actual answer is 30 degrees Fahrenheit per minute. All right, number 2, centered interval method. So we know that that is going to be between 4 and 6, right? Because that middle number was 5, and we're going to go 1 down and 1 up. And that's just simply like if this was, say, for example, 4.5, and then this would be like 5.5 type of idea, because that would be like a difference of 0.5 each. Then we would just use those numbers. But for this case, we have the number 4 and 6, so that's what we're going to use. We're going to use -1 and then +1. Okay, so in this case, h equals 1, and we did a plus h and a minus h. Okay, so for the interval methods, I'm just going to go IROC. This one's a little bit more direct. We're going to plug in f at 6 minus f at 4, and then we're going to divide it by 6 minus 4. So that gives us 310 minus 250 divided by 2. I'm going to save some space at the bottom. I get 60 divided by 2, and again, I get 30. This is not, I don't believe, always going to be the case, but show all your work. Okay, and B. Estimate the instantaneous rate of change exactly at 10 minutes using, let's do preceding. Okay, so let's call this preceding or preceding and following. Okay, so 10 minutes. So when we look at 10, there's nothing following. So in this case, we're going to do strictly preceding. Okay, so it's going to be the difference of 9 to 10, right? You just say like the difference in the x's. So in other words, we're going to come down here and we're going to say the instantaneous rate of change is going to be f at 10 minus f at 9. And then we're going to subtract 10 minus 9. So f at 10 is 400, f at 9 is 380. So we'll do 400 minus 380 divided by 1, which is going to be, I'll just bring it up here, which is going to be 20. 20 degrees Fahrenheit per minute. Okay, example 2. A ball is tossed upwards from a cliff that is 120 meters above water. The height of the ball above the water can be modeled by this equation. Okay, so a little bit different. We don't have a table of values. Now we have an equation where h at t is the height in meters and t is the time in seconds. Estimate the IROC of, or in the ball's height, average of the ball's height at t equals 3 seconds. Okay, so let's do preceding and following. Okay, so preceding, and then we're going to do following over here. Okay, we're just going to focus on preceding right now. So we have t equals 3 seconds. So when we think about preceding, we think about the number before is going to be changed. Oh, that's an A. Okay, so we are dealing with 3 seconds. So 3 minus, let's say that the h is 0.01. Okay, so 3 minus 0.01 to the interval of 3. So if we actually sub in, what is h at? This is going to be 2.99. So what is h at 2.99? Let's calculate that in our calculators. And then what is h at 3? Okay, without doing all of that calculator work, h at 3 is 105. Doing this backward. And h at 2.99, I get 105.1995. So now if you actually think about the two coordinates that we're using for the average rate of change, right? Because we're finding the average, we're accepting that it is instantaneous rate of change because h is so small. So the two coordinates are 2.99, comma 105.1995. and 3, 105. So our preceding is going to be f at 3 minus f at 2.99 okay, and that's going to be divided by 3 minus 2.99. Okay, so now we have 105.1995 minus 105 over 0.01. And if you notice, see this 0.01? This should always be your denominator. Okay, so I get negative 19.95, and that's going to be meters per second. So that's going to be preceding. Now let's talk about following. The following interval is going to be some number x between a and a plus h. So this time we're going to do some number x between 3 and, well, it's going to be 3 plus 0.01, so 3.01. That's going to be our new interval. So taking those two numbers, we get h at 3.01 and h at 3. Well, h at 3 we've already calculated, it's 105. And h at 3.01 is 104.7995. Okay, if you see, that number is very close to 105. So let's do f at 3.01 minus f at 3. And that's going to be 3.01 minus 3. So I get 104.7995 minus 105 over 0.01. And I get negative 0.2005 over 0.01. I get negative 20.05. Okay, and then again, that's meters per second. Now, if we want to find the actual mean, so let's go mean. What we're going to do is we're going to average these two out. So I get negative 19.95 plus negative 20.05 divided by 2. Okay, and putting that into our calculator, I get negative 40 divided by 2. I just wanted to check that I was right. And I get negative 20 meters per second. So, therefore, the IROC at x equals 3 is negative 20 meters per second. Going back up here, it is the instantaneous rate of change of the ball's height. So instantaneous rate of change of the ball at x equals 3 is negative 20 meters per second. And then that would put the solution into the context of the question. I'm sorry, these were supposed to be backward. F at 3 is 105. F at 2.99 is 105.1995. I had them reversed. That's going to be the issue if you reverse them. Now it is correct. It is a negative number, so that's correct. But if you put them this way, which is incorrect, I'm going to put a line through it, you're going to get positive. Okay, so reversing either the numerator or the denominator and not putting it in the correct order will give you the opposite sign. Okay, now let's move on to algebraic strategies. Okay, and this can be used when an equation is given. So, method 3, there's something called a difference quotient. So calculate average rate of change using the point where the instantaneous rate of change occurs and a general point very close to it. Okay, so this is going to get a little bit It's the exact same thing. It's just going to get a little bit more specific, okay, and a little bit more like theory-based. So this is actually what's happening if you need a visual, okay? So we have an X and Y axis, and we have some point, and the point that we're looking at here is, I believe, A. Okay, so instead of marking A with like point A is, instead of calling it X and Y, what we've called it is A, and then Y, we know that like another way of saying Y is f at X. So whatever A we plug into X is our A, and then f at A, which is whatever like the output is in the equation. Now, for another point, and assume that this is very zoomed in, okay, like very zoomed in. Zoomed in. So now we're going to pick a point B, and instead of calling B, again, X and Y, because that's all it really is, we're not going to call it that. We're going to call it B at the same number plus a little bit. So let's say H equals, let's call it 0.01 just for conversational sake. So A.01, comma, whatever the output is, the Y value, when we plug in A, like the letter A, 0.01 to that equation. So again, we're not calling it XY. So if points A and B are 2 points on the graph of f at x, then the instantaneous rate of change of y with respect to x at a point A can be estimated using, poof, this is the slope formula again. But we're not going to call it m equals. We're going to call it instantaneous rate of change equals. But it's the same thing from grade 9. Delta y over delta x, change in y over the change in x. So if you actually think about it, these are our y values. These correspond to our y coordinate in the point B and our x coordinate in the point A. Okay, where h is a very small number. So like you could see in our previous page, remember when we were doing like 3.01 minus 3 and we get 0.01? Well, yeah, that denominator, and as mentioned before, should always equal h. So instead of actually calculating the denominator, scratch that, throw your h down there. Okay, shorten it a little bit. Okay, and then just as a reminder, h is usually plus or minus 0.01 or 0.001. And this is called the difference quotient. Okay, as the point B moves closer to the point of tangent C, right, as that secant becomes so very small that it's almost a tangent, so point A, i.e. h becomes very small, because essentially h, what we're doing is h can approach a really small number, right? So as h becomes very small, the slope of the secant line through those points approaches the slope of the tangent line. Okay, and just to highlight a couple things on this graph, this is our point A, and remember how I said this is zoomed in? This is going to be A plus 0.01, something really small. Okay, and then this is our f at A, and then that's our point f at A plus h. Again, A and then plus 0.01. Right? And this is a difference of h, which is going to be, because this is going to be delta x, change in x, which we see here. And then this here is the difference being minus, the difference in the y's, again, delta y, which is here. So this is delta y. Using different quotient method, determine an algebraic expression that represents instantaneous rate of change at this point, a comma f at a, for the following functions. Then find the instantaneous rate of change at exactly a equals 2. So what we're going to be doing is we're going to do like the general form 4, or we can kind of call this like theory. Okay, and I'm going to show you how to do that, and then once we do like the theory or the general form, then we're going to actually sub in A equals 2. Okay, so we know from the previous slide, the change in y over the change in x, that's our slope, right? So that's like our instantaneous rate of change. What we're going to do is we're going to sub in f at a plus h minus f at a all over h. And we talked about this. Okay, we're going to sub in a plus h every time we see an x. We're going to sub in a every time we see an x. And then we know the denominator is simply going to be h, right? And then h is usually 0.01 or 0.001 and so on. So I'm going to write f of x, but I'm going to write a plus h. So I have 2a plus h squared minus 3. Then I'm going to subtract f at a. So 2a squared minus 3. Remember to put brackets around that, because in the next step, we're actually going to distribute that negative sign in because we're subtracting both of them. We're going to subtract 2a squared and we're going to subtract negative 3. Okay, and then that's over h. So I'm going to go ahead and expand a plus h squared. And if you need to see the long version of it, I'll do this first, and then we'll expand in the next line. Okay, and then this is going to be negative 2a squared, and negative of negative 3 is going to be positive 3. Okay, moving on, I will be skipping this step here, but if we have a times a, which is a squared, a times h, which is a times h times a, which is again ah, plus h squared. Minus 3 minus 2a squared plus 3 all over h. Okay, now we're going to distribute the 2 into the bracket. We get 2a squared plus, and remember this here is actually 2ah, so I'm just going to short form this to 4ah plus 2h squared, and then I'm going to write the rest of that. Negative 3 minus 2a squared plus 3 all over h. At this point, we should be able to do a lot of cancellation. So we have negative 3 plus 3, those cancel to 0. 2a squared minus 2a squared, those cancel as well. So now we have 4ah plus 2h squared all over h. So if we were to factor out the h out of the numerator, we would have 4a plus 2h over h. And at this point, we can also cancel out those h's. So we have 4a plus 2h. At this point, we know that h is a very, very, very small number. So what we can actually do at this point is sub in h equals 0. By subbing in h equals 0, this term here is going to go to 0, and we're going to have equals 4a. Okay, so bringing this up here, so the algebraic expression for the instantaneous rate of change is 4a. Now the second part of this question asks us to evaluate the instantaneous rate of change at a equals 2. So what we're going to do is we're just going to sub in 4 times 2, which is 8. So therefore, at a equals 2, the IROC is 8. All right, B, f at x equals 1 over x minus 1. Okay, so we're still going to do the same thing. Delta y over delta x, and we're going to sub an f at a plus h minus f at a all over h. So I'm going to show you how to work with this h in the denominator, okay? So we're going to have not f at a. So our function is 1 over x minus 1. So instead of x, we're going to sub in a plus h, and then minus 1, minus 1 over x minus 1, which is our normal f at a. Oops. I keep saying x, but it's a minus 1. And this entire expression is our numerator. Now, in order to work with the denominator, we have to have this, and we just put divided by h. And I'm going to show you why you do that in just a second. So what we're going to do here is I'm going to find a common denominator. So I'm going to take this a minus 1, and I'm going to multiply both the numerator and this denominator by a minus 1. And then I'm going to take the a plus h minus 1, and I'm going to multiply both the numerator and the denominator by a plus h minus 1. Okay. And then that's going to give us a minus 1 minus a plus h minus 1 all over same denominator, which is going to be a minus 1 a plus h minus 1. Okay, and don't cancel out either of these denominators. We want them, that's the whole purpose. We want a common denominator, and also we have a negative sign between the two terms in the numerator, so we can't just cancel out the denominators. Okay, and that's going to be divided by h. Okay, let's go ahead and distribute this negative sign into the second bracket. And because there is technically a positive sign in front of the a minus 1, we can go ahead and drop the brackets there. So a minus 1 minus a minus h plus 1 all over our common denominator. Okay, and we can do this divided by h. So negative 1 and plus 1 cancel out. A and negative a cancel out, and we are left with negative h divided by a minus 1, a plus h minus 1. Now, instead of writing divided by h, we know that we cannot divide two fractions. So instead of writing divided by h, we're going to go ahead and multiply by 1 over h. So I'm going to go ahead and cancel out those two h's, and we're left with negative 1, right? But negative 1 times 1 is just negative 1. So we're already done multiplying. And then having the same denominator, a minus 1, a plus h minus 1. And at this point, we can no longer simplify. We're done simplifying. Okay. So because this is our general expression, we can now take it a little further and sub in h equals 0. Okay, we no longer want the h in there. And we know if we turn this into the 0, it's going to just cancel out. So we have negative 1 over, and we're going to end up with a minus 1 squared. This here is our algebraic expression, algebraic expression. It's our general expression for the IROC. Okay, now if we have evaluate IROC at a equals 2, what we're going to do is we're just going to plug in 2 for the a value, and we're going to get negative 1 over 1, which is negative 1. Okay, and remember, no matter what say like X value or A value they give you, you can sub in any number to this general expression, and it's going to give you the instantaneous rate of change at that value for any point on that curve. So example 4, at each of the indicated points on the graphs given below, is the IROC positive, negative, or 0? Okay, so height of the tennis ball, h versus time. So let's talk about A. If we draw a tangent at the point A, that's going to be a positive IROC. If we if we draw a tangent at the point B, this is actually going to be horizontal. So whenever there is a change in direction, so we're increasing and then we're going to decrease, or we're going up and then we're going down. Okay, so this is 0, and 0 doesn't have a plus or a minus. Okay, so it's 0. There's no rate of change. You guys might have learned in physics, like we momentarily, just for like that split second, so instantaneously we stop, or like the ball stops and then turns around and starts going back down. Okay, and then C, this is definitely negative. And if you're wondering where we get that from, just think of slope, right? Slope going up to the right is positive, and slope going down to the right is negative. And we always read our graphs left to right, so we always read toward the right direction. Okay, this one's a little bit trickier because we actually have to draw our own tangents. So for A, we draw the tangent. Remember, the tangent cannot pass through the curve again, so it's going to be on the outside of that curve. A is going to be negative. B is that turnaround point. B is 0. C is positive. And D, again, is a turnaround point. That'd be the tangent, so D is 0. So here's some of the summary. The average rate of change is equivalent to the slope of a secant line, right? And remember, a secant line passes through 2 points on the graph of a function. We can see that here. This is a secant line. That's IROC. Now, instantaneous rate of change is equivalent to the slope of a tangent line. Remember, a tangent line passes through a curve at 1 point. Right? Just an exact point, and that's called a tangent. The slope of a tangent cannot be calculated directly using the slope formula because the coordinates of only 1 point are known. Right? So the tangent line, we're only given this point x. Okay, therefore, to estimate the instantaneous rate of change, we can use an interval strategy. So we either use preceding and following interval method or centered interval method. Okay, so 1, 2, and then if we are given the equation, so algebraically, we can find the difference quotient. That's nice to do algebraically, it's very accurate. Okay, and the last one. As a point moves closer to the point of tangency, the slope of the secant line through those points approaches the slope of the tangent line. So as the secant line moves toward the tangent and gets closer and closer, as h approaches 0. So we looked at h equals 1, h equals 0.1, h equals 0.01, h equals 0.001, okay, and so on. We actually approach the tangent.